This is part 3 of the parallel AC-RC circuit. And in parts 1 and part 2, we made the circuit. We worked out we needed current sensing resistors to take the measurements of current in each branch. In part 2, we developed the circuit and we worked with those currents and with Pythagoras to come up with the hypotenuse, if you like to call it, or the resultant current. Once we've got that resultant current, it's time now to think about the impedance of the circuit. And really the question comes down to, what is the impedance of the circuit? Well, impedance. I'm going to show today 3 methods to determine this thing called impedance. What is it though? As I've said here, it's what the signal source sees when it looks into the circuit. So if we had an eye here looking into this circuit, it sees an equivalent AC resistance formed by the combination of, in this case, XC and R. If the circuit was purely a resistive circuit, of course the impedance would be equal to the resistance in that circuit. We've seen this before, so really just a little bit of revision here. Some people, I like this. This is from a movie, of course, Pulp Fiction. It's Zed's. Whose motorbike is that? It's Zed's. Who's Zed? Zed's dead, baby. Is impedance pronounced Z or is it pronounced Z? Well, I've heard instructors from other colleges call it Z. Personally, I call it Z. I think ultimately it doesn't really matter, providing somebody knows what you're referring to in the circuit. Here's last week's circuit, the parallel AC-RC circuit that we used with a 1K and a 0.1 microfarad capacitor. There's our 2 sensing resistors. They were the currents that we measured, and then we constructed the phasor diagram showing IC, which always leads the voltage across the capacitor by 90 degrees, but the supplied current to the circuit, IT, is going to be somewhere between IC and VC, or VR, if you like. And that's called the phase angle of the circuit. If in this case the circuit phase angle was large, the circuit would be a capacitive circuit. The capacitor would dominate. If the phase angle is small, then it becomes more of a resistive type circuit. Okay, so having just reminded ourselves about last week's lesson, let's go ahead and think a bit more about this impedance, this thing called Z or Z. Now we've seen in previous lessons that we can work out the impedance of a circuit based on, and this would be in a series RC circuit, and that would be the sum of R squared plus XC squared. And if I go ahead and I run the numbers on that, and just using the pole function on the calculator, I'd put in 1000 for the resistance, and the XC squared, we need XC, don't we? So XC is equal to 1 on 2 pi FC. I know we did this last time, but we'll do it quickly again. Just grabbing my calculator and running the numbers on that. That's going to be equal to, in round terms, 6.28 times 900 times 0.1 exponent minus 6 equals 1 on equals 1769 ohms. And that's only at that particular frequency, 1769 ohms. So I'll put here, that's only at 900 hertz. Because frequency is in the bottom part of the equation here. The frequency changes, the XC is going to change, of course. Same as if the value of capacitance changes. So that's only at 900 hertz. coming back to work out the impedance then, and look, I should really just put this asterisk next to this, and a bit of an asterisk here and a bit of a question mark. Is this how we can do this? Let's run with the figures and just see where we go. So use that same colour again, 1769. Run that on the calculator. Shift pole, this is on an FX 991 ES. Shift pole 1000, comma 1769. I don't know how clear that is on the display there. Equals, and we get an impedance of 2032 ohms, and this also gives me, using the rectangular to polar function on the calculator, also gives me the phase angle of the circuit, theta, and that's going to be at an angle of 61 degrees. 61 degrees. Alright, if you didn't know any better, you'd look at that and say, well, that worked well for us in series RC circuits, so it seems to have gone okay for this one, except I look at that 61 degrees and I immediately then look at the phasor diagram and I say, that certainly doesn't look like 61 degrees to me, so I'm starting to be a little bit suspicious about how we've done that. And I'm going to use one of the first three good methods now to show us how to work out the impedance properly. So I'll just scroll up the screen here, and what colour will we use? We'll use lively purple. Method number one. Methods. Method number one. Ohm's law. We know that R equals V on I in a circuit, and in this circuit we know the total current, we know the total voltage. So because Z is the equivalent AC resistance of the circuit, this equation becomes now Z equals, just a special type of resistance, that's all, Z equals V on I. And if you think about this circuit, we've got our AC supply, we've got it coming down through a resistor, we've got it coming down through a capacitor. They both line up so that we have different branch currents flowing in the circuit. We've got the AC current flowing in the circuit, you recall, and then we've got a branch current flowing through the resistor, and we've got a branch current flowing through that little capacitor. And just to remind me, I think we had 5.61. I had it worked out there somewhere. Anyway, we can work it out again. We know that the capacitor current was 2.9 milliamps. We know that the resistor current was 4.8 milliamps. So we have to work out the vectorial sum of those two to get the total current in the circuit. So that'll be pole, rectangular to polar again, just as easy as doing the square root of IR squared plus IC squared. Pole 4.8. Does this bring back memories? 2.9. Run those figures quickly. Shift pole 4.8, comma 2.9 equals 5.61. 5.61 milliamps. And this also gives me a phase angle. Ooh, that's interesting. 31.14 degrees. An angle of 31.14 degrees. Straight away I'm starting to see a bit of a difference between our 61 degrees here and our 31 degrees here, and I'm going, ooh, this doesn't look too promising. Now that we've got the total current, we knew that we had a applied voltage of 4.90 volts RMS into our circuit, so Z is going to be equal to 4.90 divided by 0.00561. 4.9 divided by 0.00561 equals 873. Ohms, 873 ohms compared to 2032 ohms. Ooh, guess what? This is wrong. You cannot do it this way. No. And we might even put a bit of a smiley face thing on here. Not a smiley face, but maybe a surprised looking face. I don't know, maybe this one here. Yeah, I like that. Whoops. There we go. We might put that there because this is way wrong. And we'll just put a bit of an arrow from here back into here because, boy, what's happened here? You can't do it this way. Must not use this method in parallel. Okay. Now, you might be thinking to yourself, but hang on, we've used Ohm's law, we had the other method, which, you know, for all intents and purposes was what we've always done before in series circuits, so how can I say that the Ohm's law one is right and the other one's wrong? Well, let's go ahead. I did say I'll show this 3 different ways to do the impedance, so let's go ahead and look at 2 other ways to look at the impedance in this circuit. Back to living purple. Second way. Because we only have 2 components in this circuit, just like when we had 2 resistances in a DC circuit, and we wanted to find R total, we could use a thing called product over sum. And there's nothing to stop us doing that now. We can use product over sum again. So this was for DC equivalent circuit. So product over sum here is going to be R times XC times XC divided by, and this has to be, it's an addition, product over sum. So the multiplication of the 2 variables divided by the sum of them, and it can't be an algebraic sum because it's an AC circuit with things happening out of time with each other. So therefore we have to do a vectorial sum on the bottom. We have to have the sum of the square root of R squared plus XC squared. Ooh, that bottom line of the equation looks a little bit familiar. That's sort of the same as this, isn't it? We already had an answer for that. That answer was 2032. So we could probably bring that method down. Ooh, bring him down here. And that's him here. So if I go ahead and do that, that would be 1,000 times, what was XC? 1769. 1,000 times 1769 divide by 2032 equals, he quickly punches some figures into his calculator, 1,000 times 1769 divided by 2032 equals 871 ohms. Ooh, not bad. We had 873, now we've got 871. Not bad. We're well and truly within the bounds of a small error there. Error in the practical, perhaps, compared to the theory. Alright, that's method number 2, product over sum. The third method, and I'm running out of time a little bit here, I'm going to have students coming back from lunch in a minute. Method number 3, we don't want that colour, we want this colour. Method number 3, we've learned about this thing called conductance. We haven't learned what this is, but we will. Susceptance. And finally, admittance. Conductance. I'll do these in living red. Conductance. 1 divided by R. Susceptance. 1 divided by, in this case, XC. Of course, that could be another reactive component too. It could be XL. And admittance, 1 divided by Z. So we've got the reciprocal of the resistance is the conductance, reciprocal of the reactance is the susceptance, reciprocal of the impedance is the admittance. So you say to yourselves, well, so what? They're all good, they're new terms, just some more things to confuse us with electronics. Remember we just looked at these components here, and I did say that because there was only 2 components, that's why we chose to use product over sum. You can use product over sum if you've got 3 or 4, you just got to take more bites at the cherry and do it in hunks of 2. But when you've got multiple resistors or multiple resistances and reactances, perhaps it's better to use this method, and this is the sum of the reciprocals. The sum of the reciprocals. And the sum of the reciprocals here, because we are working with a vectorial equation, we're going to need to have the square root of the conductance squared, 1 divided by R squared, add the susceptance squared, 1 divided by XC squared. And then this is going to give us admittance. Y. I should have called that a Y over there. That's actually a B. That's a G. So to convert from admittance back into impedance, we need to go 1 over. Is this sort of looking a little bit about like Ohm's law about for parallel resistors or series capacitors? Same deal, it's only the sum of the reciprocals. And if I plug the values into this and I go ahead and perform the calculations, guess what? I get 871 ohms for the impedance. So just to recap, you cannot use, you cannot use the same laws that we used for series RC circuits to work out the impedance with this type of circuit, which is a parallel circuit. You have to use either Ohm's law, and that's the most commonly one that's used. Once you've worked out the total current, you've got a total voltage, hey, you can work out the impedance pretty quickly. But if you didn't go down that track and you just had the XC and you had the R, can you do it? You won't find this in all textbooks. You'll find it in the Hazen, not the Hazen, sorry, you'll find it in the Floyd textbook, you won't find it in the Hazen textbooks. You come down here and we use product over sum here, or the third method was conductance, susceptance, and admittance. Really getting a little bit into another subject called circuit analysis, but it's not rocket science, it's not that hard to do, and it's something which we can do easily and apply to this particular circuit that we're working with. So I think that was pretty well it. Impedance is what the source sees looking into the circuit. We know this, we've seen it before. We're looking at a parallel circuit where we've got the currents, the voltage is in phase, but the currents are out of phase. To work out the impedance, a little bit different than what we've seen before, but just think about it like other parallel resistive circuits. The only difference here is, of course, it's a resistive/reactive circuit. So we have to use a vectorial addition instead of an algebraic addition. Alright, I may even do a little bit more towards this. This will be the end of video number 3, and I may even do a little bit more with the practical and show on the bench the total current by putting a summing resistor at the bottom of the two branches. I thought I should do that. I probably should have done that back in segment number 1. I might do that as a segment number 4 and wrap the whole thing up in segment number 4. Okay, it's 1:10 past 1. I'm going to have students coming back banging at the door any second. This is Greg Moore signing off.